Hello, fellow Viz enthusiasts. I'm Nate Moracle, a graduate student from the University of Utah and a member of the Scientific Computing and Imaging Institute. Today, I'm excited to present our new method, quick clusters, which you can use to render and explore large unstructured meshes like these in real time. With this new approach, you can do all of this without the long pre-processing times of prior methods, with a lower technical complexity than prior methods, and all on a single workstation graphics card. But first, you might be wondering, what are unstructured volumes in the first place? Well, as our computational capabilities improve, many simulations are moving to memory-efficient formats that scale better to big data. And unstructured meshes are a very memory-efficient format because they use finite elements that can adapt in shape and size in order to increase resolution where it's needed and to reduce resolution where it's not needed. By doing this, simulation codes can bring memory consumption of these datasets down from petabytes of voxels to just a couple gigabytes of finite elements. So now the question becomes, can we visualize these datasets interactively now that they fit in memory? And well, normally I'd actually still say no. And that's because two main challenges still stand in our way. The first challenge is that we need an efficient way to sample our data on the GPU. And typically we use trees to efficiently locate finite elements containing these query points that we sample through the volume. Newer methods make this process fast and easy by using ray tracing units in modern GPU architectures. And these units handle all the tree traversal complexity for us, which make tracing array about as easy these days as sampling from a texture. Then, the surrounding graphics API handled tree construction for us, so we don't need to worry about that either. All we really need to give to our graphics API is an array of bounding boxes containing our elements, as well as the point and element tests that we use to determine if a point is inside one of those elements. Unfortunately, although these hardware-accelerated trees are relatively memory efficient as is, they still consume a significant amount of memory for the datasets that are as large as these. And so although our datasets fit in GPU memory, the trees required to query our data do not. Our second challenge is that these datasets exhibit a teapot in the stadium problem. Normally, we'd use an algorithm called ray marching, which samples the data at even steps into our screen. But as you can see, the objects that we're actually interested in observing here are very small relative to the domains of the simulation. Because ray marching travels a constant distance between samples, we must oversample these really large regions of space in order to adequately sample the small but important regions we're actually interested in observing. This can result in tens of thousands of samples per pixel, which prevent interactive visualization. So how can we solve these two challenges while keeping our technique simple and accessible? Well, it turns out that we can address all of these issues with a single data transformation by sorting our finite elements along a Hilbert space-filling curve. This curve allows us to quickly cluster nearby elements in space by grouping neighboring elements in memory together. So elements from 0 to n would define the first cluster, then n plus 1 to 2n would define the second cluster, and so on, and you kind of pick what that n is. This sort only needs to be done once during startup, and it can be done either on the CPU or you can do it in parallel on the GPU. And if you implement it on the GPU, this sort takes only about 2 to 3 seconds even on our largest dataset. In terms of cluster quality, these Hilbert clusters aren't perfect, but they're good enough for our purposes, and they're easy and they're fast to compute, even on really large datasets. So once we have these elements sorted, we can cluster our elements together on the fly to address our two challenges. First, let's use these clusters to reduce memory consumption. Starting with the acceleration structure, our trees currently consume a significant amount of memory because we separate every primitive into its own leaf. This results in a costly number of internal nodes near the leaves of the tree because trees grow exponentially with depth. But for exactly the same reason, if we assign multiple elements to the same leaf, we can significantly reduce the tree's memory footprint. So rather than build our acceleration structure down to the individual element, we instead build a tree over small Hilbert clusters of elements. And for our purposes, we'll call these clusters leaf clusters. For our datasets, we found that 4 elements per leaf cluster appears to be the sweet spot where we're able to significantly reduce tree memory consumption without compromising too much on performance. Next, we can use our Hilbert clusters to also reduce the memory footprint of our unstructured mesh. At the moment, the memory usage of our mesh is dominated by mesh indices, which are currently 32 bits each. Therefore, we again use our Hilbert reordered elements to now cluster elements into instance clusters, and it will become more clear why we call it that later. If one of these instance clusters reference more than 2 to the 16 vertices, then we use 32 bits per index like before. But if one of these instance clusters reference fewer than 2 to the 16 vertices, then we use 16 bits per index. And if one of these instance clusters reference fewer than 2 to the 8 vertices, then we use 8 bits per index. So we kind of adapt the number of bits per index depending on how many vertices are referenced by an instance cluster. Finally, rather than building one tree over leaf clusters, we now build multiple trees, one tree per instance cluster. Each of these trees contain leaf clusters like before, but now we also build an instance acceleration structure where we combine all of these trees together. This ends up reducing peak memory consumption during tree construction, and that turns out to be a really important thing. With this optimization, on average, we're able to cut the memory of our meshes in half. Finally, let's talk about rendering performance. As we mentioned before, these unstructured meshes often contain very small features of interest relative to the domain of the data. We tend to make these features optically dense so that we can see them, while the surrounding elements are made more transparent to prevent them from obstructing our view. Remarching fails us because it samples our data equidistantly, not accounting for optical density. But if a region is relatively transparent, then our sampling rate should be low, and if a region is dense, then our sampling rate should be high. So instead, we use a volume rendering technique called delta tracking. Delta tracking adaptively samples the volume using local neighborhood density estimates, otherwise known as majorants. All we need to make this algorithm work is to compute a set of non-overlapping majorants along our array. Therefore, we again turn to our Hilbert reordered elements, grouping them together into adaptive sampling clusters. For each cluster, we compute the maximum scalar density value of all the contained elements whenever the transfer function is edited. Then, when we go to render our data, we trace array through these adaptive sampling clusters, rasterizing the maximum density value into view-aligned bins stored along our array. Alternatively, you can rasterize these adaptive sampling clusters into a regular grid of macro cells, and then use an algorithm called DDA to step from one cell to the next. And then that allows you to not have to trace this final adaptive sampling array. Okay, so that's the method. Now let's go over some of the highlights of our evaluation. For all of these screen captures, we used an RTX 8000 and an Intel 12900K. And for our implementation, we're using Optix 7. With this hardware, we tested our method on 4 different real-world datasets. And from left to right, they're kind of increasing in size. So on the very left, we have the TAC Japan earthquake dataset. And then left middle, we have the deep ocean impact dataset. Then right middle, we have the NASA landing gear. And then finally, we have the NASA Mars lander on the very right. In terms of overall memory consumption, if we use 16 elements per leaf cluster, then we can achieve a compression factor between 1.5 and 3x. And to obtain this compression, it takes only 2.5 seconds to sort our elements on the Hilbert curve for our largest datasets, and then it takes about 4 minutes to compress the mesh indices for our 1 billion element mesh. With our evaluation, one thing that we studied was how effective our leaf clusters were at reducing memory consumption and how that affects performance. And in general, we see about a 2x drop in memory consumption as we double the number of elements in a leaf. Each time we do this, we also see about a 5 to 8% hit to performance. So your performance does go down as you merge more and more elements together, but that performance hit isn't actually that bad. These results are sensitive, though, to how effective your adaptive sampling is. So with our landing gear example, the small features are still really hard to adaptively sample, which result in more point queries and a higher sensitivity to linear searches at the leaves. So for that dataset, we actually take about a 35% hit to performance every time we cluster a pair of elements together. Fortunately, we found that our Hilbert clusters are relatively robust to varying cell sizes. And if we generate uniform tetrahedra versus highly varying tetrahedra, we find that varying cell size doesn't significantly impact performance as we cluster more and more elements together. Finally, we evaluate the improvements to our rendering performance over traditional methods. And the speedup that we see by switching from ray marching to an adaptive delta tracking method is dramatic. On the Mars lander dataset, with ray marching, we get less than 1 frame per second, and that's without volumetric shadows. But then with adaptive delta tracking, we get up to 16 frames per second with volumetric shadows included. And we see a similar jump in performance with all of the datasets that we have. So to summarize, right before startup, we first sort our elements along a Hilbert curve, which allows us to quickly cluster elements together. Then we use small leaf clusters to reduce tree memory consumption, and larger instance clusters to compress mesh indices and to reduce peak tree memory consumption. Finally, we use adaptive sampling clusters in combination with delta tracking to achieve interactive rendering performance. With this method, all data transformations can be done before runtime, even on very large datasets like the NASA Mars lander. Still, we believe that there could be room for further improvement. In terms of memory compression, we currently don't consider compressing neighboring tetrahedral pairs, but this could be done to potentially remove 3 indices and compress the mesh even further. Another issue we ran into was with our GPU parallel sort. At least with NVIDIA's Cub library, it's not really possible to sort elements in place, so we needed roughly twice the memory of the raw unstructured mesh to execute the sort in parallel. For smaller VRAM systems, this could be an issue. Therefore, it likely makes more sense to do these sorts of transformations once as a preprocess. Lastly, in terms of rendering, I believe it would be worth exploring a hierarchical DDA approach for datasets like the NASA landing gear, because normal DDA fails here to accurately represent majorants in that dataset without consuming too much memory. It would also be interesting to see a denoiser used to clean up the noise from initial frames, because delta tracking is a noisy process. Anyway, that's all I have for today. If you have any questions, please feel free to check out the paper or shoot me an email, and I'd be glad to follow up with you.